Recording started.
Okay. Okay. Today we want to look at engines. So engines are moving a gas around a PV diagram. Okay. I didn't quite line this one up right. This is a 3-step engine, but I gotta just line that. That's it. Okay. So, right, you can see we're step 1 to 2. What are we doing? It's isothermal. So what does that mean? 1 and 2. Isothermal.
Keep the temperature.
Constant temperature. There, and you can see the gas is expanding, right? Everybody see that? And then 2 to 3, what's happening? We're going straight down, so that is volumetric, right? And then 3 to 1, adiabatic, we're coming back, we're changing the temperature, volume, and pressure. That's that weird curve PV to the gamma we did, right? So this gas goes around, and in that process, it does work, right? Here, and then it takes in work there, but you can see this is bigger than that. So this area inside my PV diagram is how much work I do out of my engine. It's how much I get out of the engine. So the area enclosed here is going to tell me my work, which is in this case 10.28 kilojoules. All right, does that make sense to everybody? So that's what's going on. So engines, they go around a PV diagram. You start and you go around and you get back to where you began and you do work. Okay, like this. Let me see if I can show you another engine. Back. Here's the auto engine. Okay, I can even make it run. So this is the auto cycle. Auto O-T-T-O, but it's the one in your car, which is A-U-T-O. But this is the car engine, right? This is the piston. It goes on, you see the piston going up and down, right? You can see it comes up here. This is that isothermal? I think it's adiabatic. No, it's isothermal. So it's isothermal, and then isovolumetric, isothermal, isovolumetric. And then this, notice here there's no net work done in this process because you go back and forth over the same line. That's just the intake and exhale of the exhaust. All right. But this is the auto cycle. Okay. We can look up the diesel. It looks a lot like this, but it's it looks a lot like the one we just saw, but those are isothermals, and now these are adiabatic. Okay, so this is the diesel cycle. So it's got this exhaust intake, so that doesn't do any work. But here you get out adiabatic, which means what? So no Q, right? And then here I have pressure. So I gotta take in pressure, take in heat to increase the pressure, and then I do the expansion, and then I output the heat to cool the engine back down. So it's this process, right? Ooh, trains. What do they run? The old-fashioned trains. Now they run diesel. The old-fashioned trains. Cold because what kind of engine was it? Steam engine, right? So that's a different cycle. Let's look it up. This one's really weird. Okay, ooh, that's like out of focus, but that's okay. So this is the steam engine cycle. This one here is an isothermal. Comes down, and then it does what? Isovolumetric, isobaric, isovolumetric, isobaric, and then. So the other ones were a 4-step. This is a 5-step to go around. This is your steam engine. And really, this is the idealized steam engine. This they call this zero clearance, or without clearance. But really, you can't compress. This would compress the gas to what volume? Zero. You can't compress the gas to zero volume, right? So really, it's like this. You got to compress it, but you can't get all the way down to 0 volume. So this is the more realistic steam engine.
How do you know which line or curve is which again?
Well, here they wrote PV is a constant.
Yeah.
So it's got to be isothermal because PV equals nRT. T is a constant. If it was PV to the gamma, that would be an adiabatic.
Not the whole thing, but like you know how you're going down the line, you're saying.
Oh yeah, because this is constant volume, right? The volume doesn't change here, so that's isovolumetric.
No.
And then what doesn't change across here?
The
Pressure,
pressure.
so that's isobaric. And then isovolumetric, isobaric.
I know the curve is.
This curve is isothermal. Okay. So lots of different engines. We're going to look at one engine today. Not these. These are the ones you're going to do in your lab. You're going to do the calculation for. So I'm going to show you how to do a calculation for one, and then next week's lab. No, this week's lab. The weekend threw me off. Yeah.
Is this chapter 18 that we're in now? Or is this something else?
This is, if I pull up the textbook.
And I think we're supposed to have our test
Next
next week.
week? Yes.
Yeah.
Next week. So I'm trying to wrap it up.
Do we have any time to like review before the
Yeah.
class?
I'm hoping Monday. Well, Monday for sure. Maybe Friday. We'll see how much we get through. Today and Wednesday.
Is it formatted the same as last semester?
Yes. Yes. Same and well, either Monday or Tuesday evening we'll have a review.
Like a review night or?
Yeah, like we did last time. Last semester. Didn't we do review nights?
Yeah.
I don't know if anybody came.
I can't do one last one.
So the exam is gonna be on a Wednesday, right?
It's gonna be on Wednesday.
Could you do on Monday?
Huh?
Monday?
Monday what?
Instead of Friday night, can you do a Monday night?
I'll see what I can do. I gotta see what my wife's schedule is, my schedule, my kids.
Yeah.
You know what I mean?
Mm-hmm.
Because without me, there's no review. So I gotta work. It's gotta be my
We have to
schedule.
connect you.
Right?
We have to have you.
I'd love to incorporate all you guys' schedules, but I gotta incorporate mine first.
Worst case, can it be virtual?
Yeah, that's a good point.
I don't know if I can run teams in here.
Oh no, I don't mean like in here. Like if
Like purely virtual, or like set up a camera and make it virtual. Maybe I can Teams it on that.
You can.
So I bet I can Teams it. All right, let me see. You asked the material, right?
Mm-hmm. And by the way, did you guys figure out how to connect Canva with the Cengage?
No, I haven't even tried that.
Okay.
It's something I gotta talk to them to do, but I've been so busy. Let's see. Let's open the textbook and I'll show you where we're at. So we are in 18. Mary? And it looks like you're busy on your phone there. So we're doing 18. So we're talking about engines and entropy this week. Okay, now let's get back to what we're supposed to do, which is the
Mathematics.
oh man, I turned that off. I wanted to show you the engine. I wanted to show you the engine we're going to do today in class. Let me get it back on. Sorry about that. Okay. It's coming back, it's coming back. This is called the Carnot engine. Okay? And a little history. You guys like a little history with your physics?
Yep.
Carnot was engineer for Napoleon in his army. And he was tasked with improving the efficiency of steam engines. Why would Napoleon care about the efficiency of steam engines?
To move?
Okay. Yeah, so what's Napoleon got to do? He's
War.
fighting in Europe. He's got war,
Conquer?
which means what? He's got to move people and ammunition and guns around the country.
His army? Or
And he does it
countries?
with steam engines. right? But steam engines what? They take fuel, which costs money. So if I make it more efficient, then it costs less money and I can buy more guns, right? That's the idea. So he commissioned Carnot to come up with the most efficient steam engine, or more efficient. But Carnot didn't do that. What Carnot did was he found the most theoretically efficient engine you could have. It's named after him now, the Carnot cycle. So this is the engine with the highest efficiency. Okay? And it's got 4 steps. You can see them here. And you can see these two, this red and this blue, what are those? Isothermals. And then these 2 steps, you can see it popping up in here, these are adiabatics. Right? So it's 2 isothermals, 2 adiabatics. We're going around this way. This ends up being the most efficient engine.
Since Napoleon. To
Since
this
Napoleon.
day. To this day.
To this day, right. And the mathematics works out. We haven't found a more efficient cycle around a PV diagram than this one. Right? And we're going to figure out how to calculate efficiency. I didn't show you that yet, so I'm going to show you how to calculate efficiency. Did I show you how to calculate efficiency? I don't think so.
No.
So,
No.
this is the idea. This is the engine. Another way we can draw an engine is we have a hot temperature reservoir and a cold temperature reservoir, right? This is the hot, that's the cold. And what happens? I have one area of hot, one area of cold. I bring them into thermal equilibrium or into thermal contact. What happens?
Thermal equilibrium.
Well, heat flows, right? Until I get to thermal equilibrium. So heat's going to flow out of the hot reservoir. QH is going to come down. And QC is going to go into the cold, right? Now, normally QH equals QC. But I'm going to stick my gas in the middle here. And this is my engine. And what does it do? It siphons off work. So it takes some of that energy flow and uses it to do something good, right? To do work. Like your car engine, right? What's your car engine do? The piston compresses, expands, right? And that makes your wheels turn, which makes your car go. Right? So what's the hot reservoir in your car engine? Anybody know? What's the high temperature?
Oil.
Huh?
Oil.
Well, no, the gas is what's burning, but it's the spark. Spark creates the high temperature region, right? And then it causes the piston to expand, makes your tire roll, right? But then what do you got to do with that piston? You got to contract it again. So how do you do that? You got to take heat out of it, right? And where does that heat go?
Exhaust.
No, that's where the fuel goes, but most of the heat doesn't go out that
Just
way.
escape.
How does it escape? Yeah, it escapes to the environment through the front of the car. Anybody like, ever run out of coolant? Have you ever run out of coolant? What happens? Huh? You don't know? You know what coolant is, right? You got to put it in the car.
Yeah.
It goes to the radiator.
Radiator.
The radiator is dispensing heat into the environment. That's the purpose of the radiator, is to take the heat and pump it out to the environment. Right? When the radiator goes, or the coolant goes, you can't pump heat out into the environment, and what happens? The piston doesn't compress.
So the radiator takes it out as a carbon dioxide?
No, just heat.
Does he?
It transfers heat. Just you got that cool air as you're driving down the road, blowing across it, absorbing the heat from the engine. The exhaust takes out the carbon dioxide and stuff, but that doesn't carry much heat with it. Most of it goes out the radiator. Okay? So you got a high temperature, you got a cold temperature, you do useful work. Right? Oh, okay. Think about a hurricane. What's a hurricane do? We live in Florida. We need to know about hurricanes. Matthew, you've been here your whole life.
Yeah.
What do hurricanes do?
They destroy.
They destroy. They spin winds around and knock everything down.
Yeah.
But what do I have to have a hurricane happen?
Heat.
Hot and cold.
Yeah. Where's the hot?
Hot water.
The hot ocean. Where's the cold?
Atmosphere.
The upper atmosphere. When I get bigger enough temperature difference, the heat flowing causes a low pressure zone, which makes the wind spin, which you don't think of it, but it's useful work in terms of the engine, right? The wind spinning is the output, is the work being done by that heat flow from hot to cold. Right? So it's a natural engine, a hurricane. Does that make sense to everybody? In your body, you have lots of little engines. What are they? They make you go.
Cells.
Inside the cells, smaller. Who took bio?
Or glucose.
The mitochondria.
Mitochondria. What does mitochondria do?
The powerhouse of the cell.
Okay, what does that mean in terms of physics?
It makes them make them work, make it work.
How do they make it work? What do they do?
Energy.
Yeah, they take sugar, right?
Glucose.
They do through chemical reaction and generate heat and make useful work. So you're full of little cells, little engines, right? It keeps you warm, right? So you see these engines, they occur naturally or they're man-made, but they're all doing what? They're taking heat flow from the hot to the cold and siphoning some of that out to do work. The efficiency of an engine is how much work I can get out of the engine divided by how much heat I put into it. Now notice I'm using absolute values here because this is negative because it's coming out and this is positive because it's going in. So I'm going to put absolute values around this to get this so that it's a positive number, right? So this is a ratio. It's a decimal. All right, does that make sense to everybody? That's the efficiency of the engine. Now I could rewrite this a little different, knowing that these three quantities are related, QH, W, and C. You can see conservation of energy tells me that QH is equal to QC plus W, right? The energy coming into the engine has to be equal to the energy going out of the engine, either in terms of the cold temperature or the work. Right? So I can substitute, solve for W and substitute it in. I get W equals QH minus QC. So I get E equals QH minus QC divided by QH, or 1 minus QC over QH. So there's two efficient ways to write the efficiency. This way and this way. They're the same thing. It just depends on which is easier to calculate, Q or W. Okay, does that make sense? It's the same formula. Right? You with me, Dan? Okay, so we're going to apply this formula, this version of the formula, to this engine, the Carnot engine, and see how efficient it is. Okay. See what kind of efficiency we're talking about. No. Could I ever make an engine 100% efficient?
No.
No, why not?
Because heat is lost.
Okay, where's it lost to?
Environment.
Friction and things like that. Like there's
Even
other-
if I ignore friction,
Uh-huh.
I have to have heat flow this way to compress the gas. Right? If I took all this and went this way, what do we call that? That's an explosion. That's a bomb, right? Imagine what happens when a bomb goes off. Boom! All the heat energy goes into work, pushing it all out. Actually, there's some going in the environment because you heat up the atmosphere, but you don't bring the piston back together. You gotta be able to bring the piston back together. So I gotta deposit energy here. All right, so we can never make this equal to that, because I always have to have some of this. Does that make sense to everybody? You can see that in the formula here too. 1 minus QC over QH, right? The only way to get this 100% efficient is either to make that 0, no heat transfer, right? But that's not gonna work, okay? All right, so let's apply this idea to the Carnot cycle. So you see the Carnot cycle running there, and we're gonna calculate out the efficiency of this engine. And I'm going to turn on the light so we have more room to work. Let's see how much time we have. We might not get through all the steps. Let's see what we can do. Okay, so process. Let's call this A, B, C, D. These are my 4 points on the cycle. A to B is what kind of process?
Isothermal.
Isothermal. Which means what? Delta T is 0. That means delta U is
Work.
0. Because U is what? 3/2 nRT. Delta T is 0, delta U is 0. That tells me what is the work, what is Q equal to? minus the work. Right? You guys remember this? You with me, Mary? And what's the work equal to? For an isothermal, minus nRT, we derived this, ln V final over V initial. You remember that? You don't remember that. Stick it in the brain. We derived that in class, didn't we?
Mm-hmm.
Yeah. So in our particular case, V final over V initial would be what? VB over VA, right? So that means Q is positive then. nRT ln VB over VA. Okay, that's A to B. B to C, what is that? Oh, and this should be which T? This should be the hot temperature, right? Because this is the hot temperature, TH. Okay, B to C, what kind of process? What kind of process? A to B. What does that mean? What does that mean?
I don't remember.
Change everything.
Everything's changing. What's zero, Matthew?
Heat.
Heat. Exactly. Q is zero. So this is A to B added. Right? Q equals zero, right? That means PB VB to the gamma equals, I think it's PC VC to the gamma. That's the A to B addict process, right? Q is zero. That means delta U is equal to the work and is equal to NCV delta T, which would be what? T cold minus T hot. Right, you guys with me on that process? Okay, D to A. What is that? Mary. D to A. Oh, sorry, C to D. I want to do, you're right. You are right, I want to go C to D first.
Isothermal.
Isothermal, thank you. And tell me about it.
The change in temperature is 0.
Delta T equals 0. What else?
The change in internal energy is 0.
Okay. What's my work equal to?
Work is equal to, well, Q is equal to negative work.
Okay, Q is equal to negative work.
The work is equal to negative energy.
And which T?
Cold.
Cold.
And then it's the natural log of, but it's final over initial.
Yeah, which would
B
be
over C.
PV over VC. Right, so Q is positive that. Okay, and now D to C, Jared. Or D to A.
That'll also be a
A to B, yep. Okay, that tells me Q is 0. So delta U equals the work, which equals
NCV.
Yep.
T times the change in temperature.
And what's the change in temperature?
Would be like temperature of D and A.
Yeah, but which one's the final one?
A would be the final.
Yeah, so that's gonna be which T?
TD minus T
Yeah, T hot minus
A. Or yeah, T
T cold, right? Okay, these are my 4 steps. I'm gonna switch this to a white screen so we can work in the middle now that you've seen the diagram. You don't need to see it for a while. Okay, so those are my 4 steps. So I want to calculate the efficiency, and I can do it one of 2 ways. Efficiency equals W divided by QH, or it equals 1 minus QC over QH. Now, in this engine, not all engines, but in this engine, there's a particular way to do it. Makes it easier. If I wanted to do the first way, I would have to calculate the works on all the engines. So notice I have a work here, I have a work here, I have a work there. I have 4 works. I have to figure out Forces are positive and negative, add them up and get the total work, which is the area inside that curve, right? I could do that and then divide by QH. Or for this particular engine, it's a little nicer to use this version of the formula because I only have two Q's. Right, which ones? A to B, C to D. Those are the only ones with Q's. So that becomes easier. I just got to figure out which is QH, which is QC. Right? Well, which one's QH, do you think?
The one with the TH.
Well, the TH, yeah. So this is QH. This is the absorbing heat, right? And then this is the output of the coal. So I just need to put it in this formula with QC and QH, and I get the efficiency. So we'll do that. So E equals 1 minus QC, but notice it's absolute value. So NRTC ln VD over VC divided by NRTH ln of VB over VA. Okay, so I could simplify this, right? What cancels? Matthew, what cancels?
NRT. Wait, I like NR.
Close.
NR.
NR. The NRs are the same. The T's don't cancel. Right? So you get 1 minus. Now,
Can,
go ahead. Shoot.
no.
TC, TH. What do you know about these T's? What units are they in?
Celsius or Kelvin.
Kelvin. They gotta be in Kelvin. They can't be in Celsius. So what does that mean in terms of their sign?
Positive.
Positive. So I can pull them outside the absolute value. So I have 1 minus TC divided by the ln of VD over VC divided by TH ln of VB over VA. Alright? Now, this looks pretty good, but I can simplify it a little bit more by using the relationships. Because notice I got a ratio of volumes. So look, if I look at D and C, how are those related? PV and VD and VC. If I go back to my picture of the Carnot cycle, and this was A, B, this is C and D, right? How are those connected? That's an isothermal. What does that tell me?
It's like a 1 over curve, right?
Yeah, 1 over curve. So that tells me that this is PCVC is going to equal PDVD, right? Or, yeah, and these are both equal to NRTC, aren't they? PV equals NRT?
Is that PCVC equals PD, VD?
Oh, VD, thank you. Yeah. And same thing up here, right? PA equals PV VB equals NRTH. Correct? Are you with me? I just used the ideal gas law. Now, these here, these are connected by the adiabatics, which I have one over there. I need to write the other one. The other one is PD VD to the gamma equals PA VA to the gamma. So I'm going to need these in just a minute. Okay, I want to go back to my white screen. And there's Chick-fil-A. PVA appropriate. Okay. I can replace, let's replace VD and VB. Right, VD, VC. PC. Oh, I think I want to use this one. Yeah, so let's work with this equation first. I gotta do some algebra here to get this to work out right. So PB VB to the gamma equals PC VC to the gamma. If I write the pressures on one side and the volumes on the other, I get PB over PC. What does that equal? VC over VB, but this is to the what? To the gamma, right? Did everybody see that? If I do the same thing over there, PD over PA is equal to VA over VD to the gamma. Okay. So I need a VB over a VA. So we got that and that. I'm trying to remember how to do the algebra. Sorry, I gotta remember.
You put ln, so that you go to the power of Euler.
No, not yet. Gamma's 5/3, right? No, let's just divide. PB over PC. So, if I take this equation, divide by that equation, what do I get? I get PBVB divided by PCVC equals what? VA divided by PD VD. And that's equal to, this one is that one, right? That's NR, which one's PC? This one. NRTC over NRTH. Trying to remember how to do this. Oh. Wait a minute. I want a VD over VC. Don't I? Crap, I'm sorry, I forgot the algebra. These come out really nice if you can remember the algebra. They come out to 1.
Wouldn't it be like VC over VB to the power of gamma minus 1?
I think so.
Do we need to remember the algebra?
Huh?
Do we need to remember the algebra?
Well, it's going to make your life easier later. This is the net result. These cancel. And you get this. So, yes and no. No, you don't need it for the homework or the test. Yes, you want to kind of know how to do it for the engine diagram.
Okay.
Does that make sense? Because you're going to be doing this for your engine diagram. So this is the net result for the Carnot cycle. I'm just having a brain freeze on how to get those to cancel. And I know you got to use these. But I forgot how to do it now. All right, I will look it up for Wednesday, how to do it.
What we're trying to get to is the E equals 1.
Yeah, this is what you get for a Carnot engine.
I think I have an idea though.
Yeah, there's some algebra I'm missing. You got to
Like-
substitute something in. It's got the gammas.
What if you break that part, that formula over there, PBVB, PCVC, and you break PB divided by PC in VC divided by VB to the power of gamma. So see, you're gonna use those equations there, Yeah. So you cut it in half. You're gonna have PB divided by PC, and you're gonna write that in VC divided by VB.
That might be it. So that's what PB divided by PC is VC
Yeah.
over
Yeah. You write like that.
CB to the gamma.
Yeah, and then you multiply.
PB over VC
Yep.
equals the same thing over here.
Exactly. VA divided by VD to the gamma. Yep.
V VA over VD. So I get VC
Yep.
over VB, VC over VB to the gamma minus 1, right?
Yep. And then the other side, you're gonna have the same gamma minus 1 if it's right.
Oh, wait, no, this is flipped. Isn't it?
Yeah.
I want VD, because I want PA, right? P over
It should be
PD.
the same.
So it's flipped.
Yeah.
it's
So you
P
should
over-
have gamma minus 1 on both,
Yeah.
and ln of gamma minus 1 to ln of gamma minus 1 is gamma minus 1 and gamma minus 1.
So that means VC over VB is equal to VD over VA. You might have gotten it.
Yep.
Look, hold on.
Yep.
Did you got it? Did everybody see what we did? We substituted in this PB over PC
Mhm.
is VC over VB to the gamma.
Mhm.
VC over VB to gamma, and then I have a VB over VC. And I did the same thing over here. PA over PD. Well, just flip it. That'd be VD over VA to the gamma. VD over VA to the gamma times VA to the divided by VD. Now, since this is VC and there's 1, I subtract it, and then VD minus 1. So this becomes gamma minus 1. And this also becomes gamma minus 1.
And you have the ln, so it's gonna be gamma minus 1 divided by gamma minus 1.
Yeah, or just look at the inside. Because they're the same power, they have to be equal because they're inside.
Yep.
You with me, Mary?
Mm.
I replaced this
I mean, I'll figure it out.
with that. Okay, well this is the steps.
It'll make sense.
Now, if you look here, I got a VC. Oh, I gotta rearrange it. Because I need VD over VC. So I gotta bring that one there, and I gotta flip these two.
Yeah.
So VA over VB is VD over VC. And so now I can write this as 1 minus TC ln of VD over VC divided by TH ln of VB over VA. VB over VA is VC over VD. And you say, Dr. Browning, those are the opposite. Right? That's D over C. That's C over D. But what can you do with ln of x to the minus 1? What does that equal? What's x to the minus 1 mean? 1 over x. Right? And so that's 1 over x. ln of 1 over x. But that is equal to minus ln of x. Right? Because you bring the power down. So I can flip this by bringing the power down. 1 minus TC ln of VD over VC divided by TH minus ln of VD over VC, because I flipped it, but it's inside an absolute value, so what do you do with the negative? It doesn't matter. So now they're the same. And they cancel out. You saw the output. Good job. Anyways, you want to do this for your own engines. Steam engine, diesel engine, Auto cycle, Stirling engine. All these different engines have different cycles. And so you want to do them for your own. Yeah, well, you'll get in groups. And it's a really good process because it teaches you all these steps and how they're all related. Like, how does isothermal, and what are all the pieces of adiabatic, and what is the pieces of isochoric, and how they're connecting the processes. So it's a good practice. I'm not going to ask you to analyze an engine on the test. That would be too involved. But I might say, given a Carnot engine, you should know the efficiency of a Carnot engine because it shows up a lot. And we can ask, what's the efficiency, what's the work, what's the QH, stuff like that. Okay. So this is the most efficient engine. So any other engine that's running between those hot and cold temperatures aren't going to be as efficient. This is the top efficiency here. Right? So let's say we got, T hot. I don't know, what's the temperature of a car engine? Oh, someone look it up for me. My phone's there.
Efficiency of the car engine.
Well, look at the high temperature. The hot temperature of the spark in a car engine. And we need it in Kelvin.
So all cars nowadays use the same model, right? The Corvette.
The auto or the diesel?
Both use the same engine model.
What do you mean?
You know the Napoleon one that you said?
Oh, that was this Carnot engine. Yeah, cars
Carnot.
don't use Carnot engines.
Oh, they don't.
No, because in order to use a Carnot engine effectively, it has to be super slow. Like a really slow, which is not good for cars.
Yeah.
Because you want the power output fast.
Fast.
It says 105 degrees Celsius.
Okay,
Right?
that's the high temperature?
It says average engine temperature typically ranges from 75 to 105. Are you asking about like the spark?
The spark, yeah, I want the spark temperature. Because that's going to determine my hot. And then my cold temperature is outside, which is like 23 Celsius. I'm guessing like 300.
500 to 800.
Okay, so let's say 500 Celsius, right? So we need 500 plus 273, that's going to be TH, and T cold would be room temperature, so it's 273 plus 23. So the efficiency, if a car engine was a Carnot engine, it's not, but if it was, we'd have 1 minus 273, that's 293, divided by 500, that's 773. So 293 divided by 773, 1 minus that, what do you get? Sarah. I saw you had a calculator. This is if your gas engine was a Carnot engine. You get this efficiency.
0.62.
0.62. So you would get 62% efficiency. But car engines aren't that efficient. That's pretty good. Car engines are running around
30.
low 20s. Low to mid 20s. So think about it, when you buy gas, what are you doing? You go to a gas station, you're buying gas, you're buying energy. 25% is going to be used to move you. 75% is going to go where?
Today.
To the radiator, to the environment. So 75% of what you're buying, you're just dumping into the environment. Roughly on a car cycle. Right, the car engine.
Is it that caused the climate change or no?
Well, that's the O2 gas coming out. Then it gets absorbed by.
So that heat that is coming up from the radiator is not causing anything to the.
Well, it will heat the environment. Like in a city, you're going to get more heat than out in the country from it because a lot more cars, a lot more power. But really, it's the CO2 that's collecting
The UV light.
the UV light. Yeah. So that's the idea of what's going on. Okay. And you can see, I can never make a Carnot engine 100% efficient, right? Because to do that, what would I have to do in terms of the temperatures? If I want to make my Carnot engine 100% efficient, either I'd have to make TC what?
Really?
0, absolute 0. Well, we haven't been there yet, right? Or I'd have to make TH
Really high.
infinitely hot, right? Which would be bad for a car. Melt the car. That's hotter than the sun, right? So you can see we never can get 100% efficiency. All right. So Wednesday we're going to start entropy. We'll talk about engines. You might have homework on refrigerators and heat pumps. We're looking at their efficiencies, but I'm not going to give you a test question on it, so don't worry about it. Just do the homework on it. You don't have to know those for the test.
So which one's the refrigerators and what?
Heat pumps, which are basically running engines.
So what out of this do you need to know?
You need to know how to calculate the efficiency
Okay, so.
and what a Carnot engine is,
Okay.
and our general formula for efficiency,
Yeah.
Carnot engine for efficiency.
Yeah.
And you need to at least be able to analyze a step. Like, given this process, what's the W, what's the Q, what's the change in internal energy? You know what I mean? So you should know all 4 steps in detail. I'm not gonna ask you to build a whole engine and work through all the algebra on the test.
But like these things that we did on the side here, when we were talking about isothermal.
Yeah, all those. You should be able to list all those and use those to calculate something. Like I give you this cycle. Let's say we're expanding the gas under isobaric, right? I give you the initial temperature, find the final, whatever. I ask you the work done, how much heat is transferred. Use those formulas to do it. Right? Does that make sense? I'm not going to ask you to do all 4 and then add them all together and get the engine efficiency out.
So,
But you will in lab this week.
will we have entropy as well in the test?
Yes. We're going to cover that Wednesday and Friday. And then Monday review.
So what you could have done with this is put everything into the work.
You could have done the work. It actually is also messy.
Yeah, I mean-
Like, we didn't.
Because now there's 4 works. And you still got to calculate QH. You'll get the same answer if you work through all the algebra.
I
And,
just
and
wonder if that would make more sense in my head.
give it a try.
than-
You know, I would just love, I love to practice physics problems. So go and give it a try. Add up the works. Because then you get a total work. Some of them's going to cancel, some aren't. And then you divide by QH. And it should give you the same result. All right, I'll let you go. Have fun.
Cut the recording.
Yeah, cut it.
Then are we gonna
Thank
be in
you.
the same place with all these